This is my third video in my module on counting, in which we're going to focus on what we refer to as combinations and how they sort of compare to permutations. Okay, so recall that a permutation is a reordering or rearrangement of a certain number of objects, given a certain number of total objects. When we consider combinations, a little bit different. We're considering the total possible number of outcomes to, say, an experiment in which order doesn't matter. Okay, we refer to these not as permutations but combinations. Examples of this might be, we've said in the past, like if we had 8 runners and 3 of them, were to finish in a race first, second, and third, it'd be like, well, first, second, third, we had 8 runners could come in first, 7 in second, 6 in third. But this is not the idea we mean in this instance. We say order does not matter. If we had, like, say, for example, a poker hand, there's 5 cards in a poker hand, but essentially it wouldn't matter what order you were like holding your cards in, when it comes to making your hand. Okay, so if we were to now consider something where order doesn't matter, we're referring to combinations. So look at an example where combinations applies. We say, suppose a dress designer wishes to select, say, 2 colors of material to design a new dress. Okay, so she on hand has 4 colors to choose from. It says if the designer wants to use exactly 2 of the 4 colors, how many different possibilities exist for a situation. Okay, so we say we have 4 colors. We say maybe color A, color B, color C, color D, and we'll refer to it as letters instead. But basically, how many different color dresses could we make? And you could see that if we were to choose like a dress with colors A and B, here's my dress. Maybe we could say, I don't know. I get bored. I make videos sometimes here and say, here's the dress. We say A and B. It wouldn't matter if you made a second dress. I'm not going to draw a second dress, but it had colors B and A on it because it'd be the same color scheme. Okay, so if order doesn't matter, then we could say, well, let's come up with a way to do this. We could say, well, AB, AC, AD. Those would be those colors there. I suppose we could do a B with a C and a B with a D, those exclusively. And we've got one more possibility, I suppose, and that would be like a B and a, no, we already did B and D. We say C and D. C and D, this would be our other possibility. So instead of, we could say 12 total ways to do this, we say we have like 6 total ways to do this. We 6 dresses, what we could come up with here. So there's a way to calculate this in general using permutations, combinations, and that's what we'd like to get into in this video. Okay, so we say the difference between a permutation and a combination is that order does matter with a permutation, but when we talk about combinations, order doesn't matter. Okay, so we refer to a combination as this. We say a selection of distinct objects with regard to order, without regard to order, is referred to as a combination. So kind of like a permutation where order doesn't matter. And so we say, well, how do these two things like match up? Well, we say, in the last example here, we say, well, what if order didn't matter? We had come up with, say, AB, AC, AD. We also had BC and BD. We also had CD. Okay, these were our possible outcomes. So if we talk about if order matters here, we say not only would I have AB, but I would also have to accept that BA would be a different one here. We say AC, we say CA. If we had AD, then we'd have to accept that DA would be different. And you could see that basically if we were to flip our entire list around, we present a situation that is similar to the first one here. However, we've got reversals as being different things because order would matter in a permutation sense. So you could see that in this instance, there's actually twice as many permutations as we have for combinations. And so here's the interesting thing about it. We could still go ahead and do a permutation formula for this. Like in the previous video, I said, well, we have 4 different colors. How many different ways could I select? Say, 2 of them. And that's what this situation is here. We say, well, it'll be 12 total ways, and here's how we get it. We say 4 times 3 times 2 factorial, which is our, 4 factorial. Over now we have 4 minus 2 factorial, which is in this instance 2 factorial. And these would cancel out. We're left with 12 ways to do this, which of course there are 12 ways to do it. We see this over here. But in this instance we divided by 2 to get 6 possible ways to do the combination. So we say, well, how would a combination compare to this? Well, we say 4 combined 2. We'll see the combination formula on the other page in just a minute, but it's basically, for choosing 2 is written the same way. We still have 4 factorial on top, and it looks like this: 4 minus 2 factorial. We build in an extra 2 factorial. We'll explain this in just a minute, but basically we get 4 factorial over 2 factorial, 2 factorial. Okay, so basically the same thing as our original permutation. We could look at this as really just our original permutation divided by an extra 2 factorial, which gives us this expression here, divided that out. Because we had been choosing two things, so we have to divide out the reorderings of those two things. So our formula here for combinations looks like this. We say the number of combinations of just R objects selected from a total of n objects is denoted by n with this capital C and then a little subscript R. And is given by the value of this formula. So we say, well, notice here that our formula is pretty much identical, almost, we say, to our permutation formula, which was this. Perhaps we use a blue here. We say n permuting R, recall, was n factorial over n minus R factorial when you're rearranging things. This has just an additional R factorial built in, and if we had to list out what these things mean, let's write this down. We say n is the total number of objects here. We say R factorial is the number being chosen, okay? And what I mean by number being chosen, the number of the n objects out of which we are going to choose from. And then this is just our other difference here. And one thing I do want to mention about this formula is kind of nice is this. If we were to take these two numbers on the bottom, say underline, double underline the R, and the n minus R is single underline. But if you were to add them, so like R plus n minus R, we could drop the parentheses here. We get R plus n minus R, and you can see that your R's cancel out. You just get n, and not that that's a huge deal, but basically what it does imply is this. These two numbers down in the basement should always add up to the top number, which is, we'll see that here, okay? So let's go ahead and take a look at a few instances where we'd use combinations as opposed to, say, permutations. So we say, okay, example 9, how many different combinations of 4 objects are there taken 2 at a time? Well, we saw that that was 12 from the first page, but we'd get this, we'd say 4 choosing 2 at a time. We're choosing, order doesn't matter here. We say, okay, well, we get 4 factorial over 4 minus 2 factorial, but also this time we have to build in the extra 2 factorial for this guy here. So simplifying this, we get 4 factorial over 2 factorial times 2 factorial. And so this is our combination. We do need to evaluate this. A few things I do want to say about this. You're not allowed to do this and call this a 2 factorial and a 1 factorial. That doesn't work that way. And also in the basement, we're not allowed to say, 2 factorial times 2 factorial equals 4 factorial, because this is just simply it's not true. So that doesn't happen that way either. We actually have to write out what we mean. And so notice that we have 2 factorials in the basement. If we were to write all this out, it would mean essentially this here, over 2 times 1 times 2 times 1. And so we've got this here, and you can see that one of these would cancel out with the 2 and the 1, but the other part of this we'd actually be left having to simplify on our own, like the 2 and the 4 share a common factor of 2. This would be 2 and this would be 1 if we reduced it. And I would always recommend this, circle what you have left on the top. So we have 2 times 3, and we get our 6, which was, exactly what we had seen in this instance here, 6 possibilities. But essentially we did this with the formula instead. So one thing I want to mention is this, since we're counting things, like, if you had 4 objects, how many ways exist to rearrange 2 at a time, okay? Or not rearrange 2 at a time, but choose 2 at a time. Consider this, you're never going to answer that question like, 12.7 ways to choose 2 objects at a time from 4 objects. So you're never going to get a decimal with this, and if you're not going to get a decimal, everything in the bottom must cancel. It must cancel out with the top when it comes to at least counting type of situations. There may be factorial expressions that I could give you that come out to be, decimal value, but in this instance, we're saying, we get a whole number of values. So let's look at examples 10 and 11. We say, example 10, a bike shop owner has 12 mountain bikes in a showroom. So 12 total things. Wishes to select 5 of them to display at a bicycle show. So it doesn't matter what order they're sitting in at the bike show. We just need 5. So in that case, we say, well, n, in this case, we've got 12 total bikes, and we only want to choose 5 at a time. So our combinatorial expression looks like this, 12, choosing 5 at a time. So again, very, very permutation-like. We say 12 factorial over 12 minus 5 factorial, but we have to build in an extra just 5 factorial here. Which, by the way, simplifying, we get 12 factorial over, let's see, it was 7 factorial. Of course, this would have to be a 5 factorial then, because they add up to be the top number. But simplifying this, you ask yourself, well, which one of these on the bottom, the 7 or the 5 factorials, has the biggest capability of taking out as much of this 12 as possible? And so if we were to write this out, I'd say, well, the 7 would. And the reason why is because 12 times 11 times 10 times 9 times 8 times, we could say 7 factorial over this 7 factorial times 5 factorial. We say, well, these would just wipe each other out. And so I'd still have to reduce this. This is the unfortunate thing about using combinations off of a calculator. We can do this on a calculator. But we have to write it out. So we have this here. And I'm not going to write the 1 down here. It doesn't matter anyway. So we say, let's take out this 2 actually with a 12. It's always good to take out bigger numbers first. So like, for example, the 3 and the 9. I suppose that this would turn into a 3. The 4 does go into 8 twice, and then the 5 goes into 10 twice. So again, circle what you have left over. We have to have nothing left on the bottom but 1s. We say, okay, well, 6 times 11, that's 66. Times 2 times 3 times 2, well, that's 12. 66 times 12. I suppose I've got a calculator out here. We say, all right, well, 66 times 12. 792. So we have 792 ways that we could display 5 bikes if I had 12 total to choose from. And then the last one here, we say in a club there's 7 women, 5 men. It says a committee of 3 women and 2 men is to be chosen. How many different possibilities are there? This sounds like really interesting. And the reason why is I want to actually consider our sample space here. We've got 12 total people, total. And so the thing is, we say a sample space of size 12. It seems that we have slightly more women than men. We say women, we have 7 total, and men, we have 5 total. The thing here is this, we say a committee of 3 women and 2 men. And so, you know, we see this word and here, which would imply kind of like a multiplication sense. But the thing is this, we need to choose a woman first. That constitutes our first event. Sorry about the weird handwriting there. And then we need to choose a man. And so since these are 2 events, we're actually going to invoke the multiplication rule. It says, well, let's find the number of ways there exist to do the first thing, and then take that times the number of possible ways to do the second thing, and that's the total number of possible ways to do it. In this case, we see this. We say we're going to go through a category at a time over here. We say of the women, you know, we say there are 7 total women. So that's our n there. We say how many do we want to choose for a committee of women? We say 3 women. So we say of the 7 women, I want to choose 3 of them. Order doesn't matter. And then we'll choose a man. We say how many ways exist to choose a man? Well, you know, if I have 5 men, and I want to choose 2 of them, that's my committee of 2 men, we say we've gone through the second category over here, which was the 5. We say, and of those I wanted 2. So we can just multiply these together. As a matter of fact, writing this out, let's see, all out, we say 7 factorial over 7 minus 3, which would be 4 factorial times 3 factorial. All of that now times, it'd be 5 factorial, 5 things, 5 men. 5 minus 2 is 3, so 3 factorial times 2 factorial, those add up to 5. So now writing these things out, we say, okay, well, we've got a 7 times a 6 times a 5 times a 4 factorial over 4 factorial times a 3 factorial, where the 4's wipe each other out. And then over in this expression, we have a 5 times a 4 times a 3 factorial over 3 factorial, 2 factorial, where the 3's wipe each other out. So going a step further, I'm going to bring it over here and then we'll be done with this. We say 7 times 6 times 5 times 5. I'm going to go ahead and combine it with my next numerator, times 5 times 4. And this is all over now, you know, 3 times 2 times 1 times 2 times 1 in the second denominator. So wiping things out, we say the 2 and the 6 here, you know, it'd be like a 3, or the 2 and the 4 is make this a 2, and the 3 wipes out with this 3 perfectly, and it's gone. So we have 7, 1, 5, 5, and a 2. So 7 times 5 is 35, we have 35. And we say 5 times 2 over here is 10. We've got 350 ways to do this, but the important thing is to recognize that we may do this with the multiplication rule sometimes, and it still works, okay? Just treat this word and like multiply. So cheers.